Alright, so basically, what has been found is that generally it's called the asymptotic behavior of a rational function. So basically, when you have a function that nears some horizontal asymptote, so in one direction, so here's our horizontal asymptote, okay? It depends. So this behavior, like what it does as it approaches infinity or negative infinity, it depends only on the leading terms. Okay, so behavior at asymptotes depends only on the leading terms of numerator and denominator. Okay, and leading terms meaning with the highest degree, whatever term has the highest degree. So numerator and denominator. Okay, so let me give you an example of what I mean. So let's say that if we have this if a sub n and b sub m are not equal to 0, so these are just coefficients, okay, then we have that the following limit, so this is going to be kind of a long limit, x as x goes to positive or minus infinity, plus or minus infinity of a sub n x to the n. Okay, so again, a sub n, that's going to be a coefficient of our x to the n power here, of that term, and then a sub n minus 1 times x n minus 1, okay, and then going along, and we have a bunch of terms. This is a polynomial, okay, until we get a naught, or a 0, okay, and then on the bottom, what we'll have is kind of something similar, but now we'll just use m's instead, okay, so now we have something like this, m minus 1, x to the m minus 1, and then continuous terms, and then we have a b naught over there. Okay, so basically what this is saying is that the behavior in the long run, so as x goes to plus or minus infinity, depends only on the leading terms of the numerator and denominator. So in this case, what are the leading terms? Well, if we assume that a sub n and b sub m, the coefficients here are not 0, then these two here would be the leading terms, okay, because I wrote them in descending order. So n is the highest degree on the top, so that makes this term here the leading term, and m, as in mouse, is the leading term, or is the highest degree on the bottom, on the denominator, so that makes this the leading term as well, okay? So, for example, if you were to have like an x to the third minus 2x plus 1, okay, then your x to the third would be your leading term on the top of the numerator, and then everything else, the minus 2x and then plus 1 or what have you, those would basically go away or become very insignificant in the long run. So these terms here, the ones succeeding the leading terms, these would become, well, definitely the constants go away as everything else goes to infinity. These ones go away. These middle ones here, they're not big enough, okay? And even this one here, those would go away as well. We just kind of ignore those, all right? So what we're going to have instead is just take this, pull this out. And this is only, again, you can only do this, like ignore the other terms, when we're observing limits at infinity, okay? All right, so what this turns into is a limit as x goes to plus or minus infinity of a n times x to the n over b sub m x to the m. So since these are constants, we can just pull them out, right? So now we'll have a sub n over b sub m, and then times the limit as x goes to infinity. And another way to write this is just to subtract the coefficients, right? If you have something divided by something, then we could write as x to the n minus m. Okay? So that's basically it. And then on the next slide, I'll show you a little bit more in detail about what could happen with this, with regards to this last boxed thing. Okay, so I'll just write that down here again. So a sub n over b sub m, and then limit as x goes to plus or minus infinity of x to the n minus m. Alright, so we have a couple different cases of what could go on. So I'll give you some examples of what they could be. So example 1, so let's say we have the n equals m case. So what does that mean? So let's say we have limit as x goes to plus or minus infinity of 2x to the fourth plus x to the third, and this is over 5x to the fourth minus x squared minus 1. Okay, so according to our formula up here, according to this formula there, this is going to, in the long run, so as we're observing the limit as it goes to infinity, the leading terms on the top, on the top and bottom are 2x to the fourth and 5x to the fourth respectively, right? So that means the other terms, we can kind of ignore those, and we'll pull out the coefficients, so 2 and 5, so 2 over 5, this is our a sub n, this is our b sub m, okay? And then we have it multiplied times limit as x goes to plus or minus infinity of x to the 4 minus 4, okay? So that's a 0 up here, so that means this is a 1, all right? Well, okay, yeah, I'll take it slowly. So this is a 0, so then we get 2 over 5, and then times the limit as x goes to infinity, plus or minus infinity of x to the 0 power, and when we have an x, anything to the 0 power, we just get a 1 there. So this limit is just going to turn into a 1 overall. Okay, so we have 2 over 5 times a 1, so that's just going to be a 2 over 5. Okay, so that was the case when n is equal to m, and in this case they are both 4s. Alright, and then let's do another example. What else could happen? So here's example 2. What if n is greater than m? So let's look at one of those. So let's say we have limit as x goes to plus or minus infinity of 2x to the fourth, and then plus our x to the third, over, this time it's a 5x to the third minus 1. Okay, so let's look at this. We're going to do the same thing. So the leading term on the top, on the numerator, is our 2x to the fourth. The x to the third will go away in the long run. And on the bottom, our leading term is 5x to the third, and then the negative 1 will go away in the long run as well. So this turns into a 2 over 5, limit as x goes to positive or minus infinity. And then we have an x to the 4 minus 3, n minus m, 4 minus 3. So this is going to be a 2 over 5, limit as x goes to plus or minus infinity of x to the 1 power. Okay, so I'll continue this on the next slide. So if you look at it, what we get is a 2 over 5, and then if we were to plug in that plus or minus infinity, and that's to the 1 power, then we get something that is actually just infinite, right? So it would turn out to be a plus or minus infinity, depending on which one you're looking at. So if we're considering both, it would just be plus and minus infinity, okay? So that's the case when n is greater than m. And in a more like, I guess, logical sense, this n is greater than m means that the degree on the numerator, the highest degree on the numerator, is greater than the highest degree in the denominator. Okay, because remember, our n's are on the top and our m's are on the bottom. Okay? Alright, now for one last example. Okay, so example number 3. So what other case could we have is if n is less than m. Okay, so in this case, this means that well, I'll show you in the example. So let's say we have a limit as x goes to plus or minus infinity of 2x to the fourth plus our x to the third, and then this is over x to the sixth plus 2. Okay, so let's see what happens here. So basically what we'd have is our leading term on the top is 2x to the fourth, x to the third goes away. The leading term on the bottom is x to the sixth, the 2 goes away. So we're going to pull out a 2 and a 1, 2 over 1, and then have that multiplied times the limit as x goes to plus or minus infinity of x to the 4 minus 6. Okay? So this is going to be a 2 over 1 times limit as x goes to plus or minus infinity of x to the negative 2, which is 1 over x squared. And then this let's analyze that. So we have a 2 times, and then if we plug in that plus or minus infinity, then we get squared here. So this is like 1 over infinity, which turns into a big 0. So 2 times 0 is ultimately 0. Okay? Alright, so that's the last case, and this was, again, n is less than m, implies that the highest degree on the numerator is less than the highest degree in the denominator. Okay? Alright, so that's it for this section, and I hope that helped, and good luck on your homework. Así que fe, amor, no necesitas